A 0.5 Tesla magnetic field is directed into the page. A particle of mass 5 times 10 to the negative 20 kilograms and charge 3 microcoulombs enters the field from the left side with a speed of 4 times 10 to the 6 meters per second. So if that represents our magnetic field going into the page, and we have a charge moving into the field from the left side, in part A, what are the magnitude and direction of the magnetic force that initially acts on the charge? So it's just the equation for the force on a moving charge, F equals QVB sine theta, where the sine of theta is 90, so the sine of theta is just 1. So it's just going to be QVB. The Q is 3 microcoulombs, or 3 times 10 to the negative 6, times 4 times 10 to the 6 meters per second, times the magnetic field, which is 0.5. And you can see the 10 to the negative 6 and 10 to the positive 6 cancel out, and this just leaves you with a force of 6 newtons. What's the direction of that force? If you do the second right-hand rule, put your fingers in the direction of the charge's velocity, which is to the right, curl them into the page, and your thumb is pointing upward. So when the charge enters the field, it starts on what would be a curved path going upward. And again, to be specific with writing this, you should say upward toward the top of the page to differentiate it from upward out of the page. For part B, determine the magnitude and direction of the electric field that would need to be applied in the same region as the magnetic field in order for the charge to move through undeflected. So the force due to an electric field is just Q times Z. We want the forces from the magnetic field and the electric field to balance each other out. So the force from the electric field has to exactly equal the force from the magnetic field, which you just got as 6 newtons. So I want to rearrange this equation for E, which is F over Q, take the F that we just solved for, this 6 newtons, divide by the charge, which is 3 times 10 to the negative 6, and that gives you an electric field equal to 2 times 10 to the 6. And the units of electric field are either newtons per coulomb or volts per meter. And what's the direction of the electric field? It's much easier to figure out than for charges, because for a positive charge, the direction of the field is in the same direction that you want to apply the force. So since you want to apply the force downward toward the bottom of the page to cancel out the upward motion, you can just say that is also the direction of the electric field, downward toward the bottom of the page. For part C, if the particle entered the magnetic field at a faster speed, but the same electric field determined in part B were still applied, in which direction would be the initial force on this particle? So, changing the speed would only change the magnetic force, since the magnetic force is QVB sine theta, which we'll leave off, and the electric force is QE. Changing the speed would increase the magnetic force, so it would be a stronger upward force, which means that the particle would go toward the top of the page. And your justification could just be, since the FB, which is upward, is now greater than the FE, the force due to the electric field, which was downward. And for part D, if instead the particle entering the magnetic field had a charge of negative 3 microcoulombs, would it be necessary to apply the electric field in the same or opposite direction as in part B in order for the charge to move through undeflected. If the charge is negative, that means the initial force due to the magnetic field would be in the opposite direction. So as the charge entered the field, it would actually be deflected downward. So most people's natural instinct is to say that the electric field should be reversed, but that's not the case, because when you have a negative charge, the force due to the electric field is also in the opposite direction. So the force due to both fields would be in the opposite direction, which means that you wouldn't have to change the direction of the electric field. The changes from both forces would end up canceling out, so you actually have to apply the electric field in the same direction. And for your justification, you could just say that the forces due to both fields would be reversed.